Welcome to our International Payments Portal. On the back end, we are using Node.js with Express as our web framework. For our database, we chose MongoDB Atlas. On the front end, we are using React.
When an employee navigates to the login page, they are presented with a simple but secure form asking for their username and password. All user input is validated on both the client and on the server. We use JOI validation schemas to check that the username follows a valid format. When the employee submits their credentials, the request goes through several security checks. The first of these is a rate limit check. This prevents brute force attacks. On the server, we retrieve the employee record from the MongoDB database and use bcrypt to compare the resulting hash of the submitted password with the hash that we have stored in the database. If the submitted credentials are valid, a JSON web token that contains the employee's user ID, username, role, and a session fingerprint is generated. The fingerprint is a hash of the user's browser information and IP address. The fingerprint is to catch if the information changes and then invalidate the token. The JWT is sent to the client as an HTTP-only cookie. The cookie also has a secure flag set, meaning it can only be transmitted over HTTPS and not regular HTTP. The same site attribute is also set to strict, which prevents the cookie from being sent in cross-site requests. After successful login, employees are redirected to complete their two-factor authentication.
Customer login follows a similar security pattern to employee login, but with additional fields specific to customer accounts. Customers must provide their username, password, and their 10-digit account number. We validate that the account number is exactly 10 digits using regular expressions. This prevents SQL injection attempts and ensures data integrity. The username and password go through the same validation we use for employees. The backend performs 3 checks, the first one being verifying that the username exists in the database. Second, it uses bcrypt to compare the password hash. Third, it verifies that the provided account number matches the one stored for that username. All 3 must pass for authentication to succeed. If any check fails, we return a generic error message, invalid credentials. Just like the employee login, successful authentication results in a JWT being created with the customer's information. Customers are then directed to the multi-factor authentication step before gaining full access to the application.
The registration process enables new customers to create accounts. Users begin by completing a personal information form. All inputs are sanitized using Express Validator to remove any HTML or JavaScript code and trim to prevent formatting issues. The registration routes, validators, and handler back-end validation with a join schema duplicates the front-end checks, ensuring data integrity even if client-side validation is bypassed. The system also checks MongoDB to ensure usernames are unique. Passwords are hashed with bcrypt, using a cost factor of 10, producing 1024 hashing rounds for strong security while keeping registration fast. Bcrypt also generates a unique salt for every password, ensuring that even identical passwords produce different hashes and defending against rainbow table attacks. Users are then guided to set up MFA and are provided with recovery codes. Once MFA and recovery codes are configured, users can securely log in with their credentials.
Multi-factor authentication, or MFA, is our second layer of security. We are using TOTP. This stands for time-based one-time password. How it works is we create a 32-character secret key that is unique to the user during registration. This secret key will then be used for generating the authentication codes. We then generate a QR code containing this TOTP secret. The QR code is then sent to the front end and displayed to the user, who then scans it with the authenticator app. Once scanned, their phone then can generate the 6-digit codes that change every 30 seconds. This means that even if someone steals your password, they still can't access your account without your phone or authenticator device. After logging in with the username and password, users are immediately redirected to the OTP verification page. The page then displays a simple form asking for a 6-digit code. This code is generated by the Authenticator app on the user's phone using the TOTP secret we created during registration. Our TOT works by combining the secret key and the current time by using a cryptographic algorithm. This then produces a 6-digit number that changes every 30 seconds. Because both the server and the authenticator app both know the secret key and can both read the current time, they independently generate the same 6-digit code. This means that the code never needs to be transmitted or stored and is computed on demand. When the user enters the 6-digit code, we send it to the backend along with the authentication cookie. The backend retrieves the user's TOTP secret from the database and uses the Speakeasy library to verify the code. We use a time window of 2. This means that we accept codes from the current 30-second time window, the previous window, and the next window. This 90-second total window accounts for slight clock differences between the server and a user's phone. If the code is valid, we then update the session to mark MFA as complete and redirect the user to their dashboard. TOTP is resistant to many types of attacks. Even if someone intercepts the 6-digit code, it's useless after 30 seconds. Even if they access our database and steal the TOTP secret, they still can't generate valid codes without knowing the exact time synchronization. And even if they steal both the password and the TOTP secret, they still need to bypass our session fingerprinting. Using MFA significantly increases the account security.
Password recovery is a critical feature, but also a potential security vulnerability if not implemented correctly. We've designed a secure 2-step recovery process using the recovery codes generated during registration. The generate recovery codes endpoint implements a generate once, show once, store hashed pattern that's considered best practice for backup codes. We hash codes with bcrypt before storage, meaning even a database breach won't expose the actual codes. First things first, we validate the input. The endpoint expects a user ID from the request and we check if it actually exists. If there's no user ID provided, we immediately send back an error saying user ID required. Next, we look up the user in our database. If we don't find a user with that ID, we return a user not found error. We can't generate codes for someone who doesn't exist in our system. If codes already exist, we prevent the generation of new ones. 2 separate arrays are initialized. The first array, code plain codes, will hold the actual codes we show to the user. The second array, hashed codes, will hold encrypted versions of those codes that we store in our database. We generate exactly 10 recovery codes. This number represents a careful balance between usability and security. For each iteration, we generate one code using Node.js's built-in crypto module, specifically the random bytes method with 4 bytes as the parameter. The crypto random bytes function uses the operating system's cryptographically secure random number generator. These 4 random bytes are then converted to hexadecimal format, which gives us exactly 8 characters. We also convert the result to uppercase for better readability. The plain text code is then added to our plain codes array. Immediately after creating the plain code, we hash that same code using bcrypt with tensor rounds. The resulting hash is then pushed into our hashed codes array. Now we update the user's document in MongoDB. Finally, we send the plain codes back to the user in the response. This is the only time these codes will ever be visible. The user can either download or copy the codes to their clipboard and save them somewhere safe. When a user clicks Forgot Password, they're taken to a page asking for their username and one of their recovery codes. After entering the username and recovery code, the backend retrieves all recovery codes for that user from the database. We use bcrypt's compare function to check if the submitted recovery code matches any of the stored hashes. We also check if the recovery code has been used before. Each code in the database has a used flag. Once a code is used, it's marked as such and can never be used again. This prevents someone who finds an old recovery code from repeatedly accessing the account. If the recovery code is valid and unused, we generate a special JWT token called a reset token. This token is different from our regular authentication token. It has a very short lifespan of just 10 minutes and can only be used for password reset operations. The token contains the user's ID and a timestamp. This reset token is sent back to the client and stored temporarily. The user is then redirected to the passwords reset page, where they can enter their new password. The reset token must be included with this request. When the new password is submitted, we validate it using the same strength requirements as registration. We then hash the new password using bcrypt with our standard cost factor of 10. We update the user's password in the database and immediately invalidate the reset token. We also mark the used recovery code in the database. MongoDB is used for our database, and it is a NoSQL database. Our MongoDB database is structured with two main collections, users and payments. The users collection stores all authentication and account information. The payments collection stores every payment transaction. MongoDB is immune to SQL injection attacks since it uses a completely different query language. However, NoSQL databases have their own injection risks called NoSQL injection. To prevent this, we're using the Express Mongo Sanitize library. This middleware automatically removes any $ and periods from user input. This is because in MongoDB, $ are used in front of operators like where, and periods are used to access nested properties. By removing these characters, we prevent attackers from injecting MongoDB operators into our queries. Our connection to MongoDB uses a connection string that includes our credentials. This connection string is stored in an environment variable, never in our code. This means sensitive credentials never appear in our Git repository or source code.
The payment creation process is a core feature of our application, designed with strict validation and security at every step. On the Make Payment page, users complete a form with details. Each field undergoes validation. The amount must be a positive decimal. The currency field is a drop-down limited to 8 supported options, preventing invalid codes and verified server-side against a whitelist. For payee and bank names, we trim white space and apply sanitation using the escape function to remove any HTML or JavaScript content, ensuring all submitted data is clean and secure. These fields must not be empty, which we verify with Joy's not empty validator.
The Swift code has to follow a specific format that we validate using a regular expression. It ensures the submitted Swift code matches this format. When the payment form is submitted, data is sent to the backend payments endpoint, which requires JWT authentication. Unauthorized requests are immediately rejected with a 401 HTTP code. Once verified, the data passes through a J or I validation schema. We never rely solely on the client-side checks since they can be easily bypassed. After validation, we create a payment object containing the submitted data plus additional fields. The user's ID and username from the JWT are added to track ownership, and the status is set to pending for employee review. The unique payment reference is then generated using the prefix pay, and then the current Unix timestamp is added on. This is to ensure uniqueness. The payment object is then inserted into the MongoDB payments collection. MongoDB returns the document's ID, which we send back with the reference number in a success JSON response. On the front end, this reference is displayed to the user and the form resets for new entries.
The Employee View Payment interface is where bank staff review and process international payment requests. This interface is done with a role-based access control, meaning that only users with the employee role can access this page. When an employee logs in and navigates to the View Payments page, React's use effect hook triggers an API call to fetch all pending payments from the database. This call goes to the /API/payments endpoint with the credentials included. This means the JWT cookie is automatically sent with the request. On the backend, the verify token middleware intercepts this request first. It extracts the JWT from the cookie, verifies the token's signature using our JWT secret, and checks that it hasn't expired. If the token is valid, it decodes the payload and attaches the user information to the request object. The route handler then queries the MongoDB payments collection using the find method with an empty filter object. This then returns all payment documents. We then convert the MongoDB cursor to an array and send it back as a JSON. The front end receives this array and stores it in the component state using the useState hook. React then renders the payments in a table. Each row represents one payment, and we use the map function to dynamically create table rows from a payments array. Each payment has action buttons that change based on the status of the payment. For payments with a pending status, we'll show approve and reject buttons. Once a payment is approved, the buttons are replaced with the Send to Swift button. For rejected payments, no buttons are shown, only the status is displayed.
When an employee clicks approve, we send a post request to the payments ID approve endpoint, where ID is the specific payments MongoDB object ID. This endpoint is protected by the verified token. It verifies that the user's role equals employee. If a customer somehow got this URL and tried to approve a payment, this check would reject them with the 403 forbidden status. The approval endpoint uses MongoDB's update1 method with the set operator to modify the payment document. We set 3 fields. Status becomes approved. Approved by is set to the employee's username from the JWT, and approved at is set to the current timestamp. This creates a complete audit trail. The rejection process is nearly identical, but sets the status to rejected. In a real-world implementation, the next step after approval will be to send this payment data to the SWIFT network for actual processing. SWIFT is the international network that banks use to communicate and transfer money. Our approved payment would be formatted according to SWIFT's message format and transmitted securely to the receiving bank. We simulate this in our application by including all necessary SWIFT information. In production, we would integrate with the SWIFT gateway service that handles the actual message transmission. One security consideration for the employee interface is that we refresh the payment list after every approval or rejection. This ensures the employee sees the current state of all payments.
Session management. Getting it right is critical to the security of the application. We're using a combination of Express Session for server-side session storage and JWT tokens for stateless authentication. When a user logs in successfully, we create an Express Session using the Express Session middleware. The middleware generates a unique session ID and stores it in a cookie that is sent to the user's browser. We use a long, random string stored in our environmental variables to sign the session ID cookie. If someone modifies the cookie, the signature won't match and the session will be rejected. We also have the Save Uninitialized Express Session option set to false, which means we don't create sessions for users who haven't yet logged in. This is to prevent session fixation attacks. We have set secure to true for production. This means that the cookie can only be transmitted over HTTPS and never plain HTTP. The same site attribute is also set to strict. This prevents the cookie from being sent in cross-site requests. This is our defense against cross-site request forgery attacks. Even if an attacker tricks a user into clicking a malicious link, the browser will refuse to send the session cookie with that request. We have a max age value of 1 hour, after which the session expires and the user must log in again. This limits the window of opportunity for session hijacking attacks. The JWT token is also stored in an HTTP-only cookie, with the same security settings as the session cookie. We use the JSON Web Token library to create and verify these tokens. The token is signed with our JWT secret, which is a different secret from the session secret. The Express Session provides server-side state management and easy logout functionality. We can destroy the session on the server immediately. The JWT provides status authentication that we can verify without database lookups, making our API much faster. When a user logs out, we destroy both the Express Session and clear the JWT cookie. We then call req.session.destroy to remove the session from server memory and res.clearCookie to tell the browser to delete the cookies. This ensures the user is completely logged out and cannot use those credentials again.
We never store passwords in plain text, only hashed versions. So even if the database is compromised, Attackers can't
an
access
algorithm specifically designed for secure password hashing. It's intentionally slow, which helps defend against brute force attacks. During registration, we call readcode.hash with a cost factor of 10, meaning a password undergoes 1024 hashing rounds. This significantly limits how many passwords an attacker can test per second. Bcrypt also generates a unique salt for every password, ensuring that even identical passwords produce different hashes. This defends against rainbow table attacks. The resulting hash string includes the algorithm version, cost factor, and the salt plus hash combined. When users log in, bcrypt compare rehashes the entered password with the stored salt and checks for a match. We also use bcrypt to hash recovery codes. SQL injection is one of the most common and dangerous web vulnerabilities, but in our case, we have an advantage. We don't use SQL. Since our app uses MongoDB and no SQL database, MongoDB uses structured JavaScript objects instead of raw query strings, so user input is always treated as data. We also validate and sanitize all inputs to ensure the database logic remains safe. We use the Express Mongo Sanitize middleware to block NoSQL attacks. It inspects every incoming request and removes or replaces keys. The sanitization is configured to run before any root handlers, ensuring malicious operators are stripped out early. We also log these sanitization events to detect repeated attacks. Input validation adds another layer of protection. The join schemas ensure submitted data matches expected data types and formats. The Express Validator library escapes special characters to prevent HTML or JavaScript in any user input from being executed. We also use safe patterns whenever user input is involved. We safely convert string IDs with new object ID, which rejects invalid formats instead of processing them. Finally, MongoDB's role-based access control enforces the principle of least privilege. Our app's database user can only read and write to specific collections, limiting damage even if an injection attempt succeeded.
We implement multiple layers of defense to prevent clickjacking. Our first layer of defense is Xframe Options HTTP header, which we set using the Helmet library. We configure it to deny, which tells the browser do not allow this page to be displayed in any frame, iframe, or any embedded element, regardless of which site is trying to do it. The Xframe Options header is supported by all modern browsers and many older ones. When a browser receives a page with this header set to deny, it refuses to render that page inside a frame. Our second defense layer is the Content Security Policy, or CSP for short. We use the Frame Ancestors Directive. This is a more modern approach to the same problem. We set our frame ancestors to none, which has the same effect as Xframe Options deny, but this is part of a broader content security policy standard. This directive is supported by newer browsers and provides more flexibility than an Xframe Options. Having both methods provides defense in depth. Some older browsers support Xframe Options but not CSP, but some newer browsers prioritize CSP over Xframe Options. By including both, we ensure maximum compatibility and protection. Our third defense layer is a frame-busting JavaScript snippet in our HTML template file. This code runs as soon as the page loads and checks if the page is being displayed inside a frame. The code works by checking if window.top is not equal to window.self. Then we know we are in a frame. In this case, we set window.top.location to window.self.location, which attempts to break out of the frame and load our page in the full window. This JavaScript approach is our fallback for very old browsers that don't support the HTTP headers. It is not as reliable as the headers because our JavaScript can be disabled, but it adds another layer of protection. Our fourth and final layer is a content security policy meta tag directly in the HTML. This provides the Frame Ancestors Directive even if the HTTP header is somehow stripped or not set correctly. Despite this being redundant with our server-side CSP header, it can be good for security reasons. This fourth layer approach means an attacker would need to bypass multiple independent protections to successfully clickjack our application.
Session hijacking is a type of attack where an attacker impersonates a legitimate user using their already authenticated session. We have implemented several measures against this type of attack. Our primary defense is session fingerprinting. When a user logs in, we create a cryptographic fingerprint of their session by hashing two pieces of information together. This is their browser's user agent header and the IP address. The user agent header contains information about the browser and operating system. This hash is unique to the specific IP and user agent combination. The fingerprint is stored in the JWT token when we create it during login. On every request to our API, we generate a new fingerprint using the same process, hashing the current request's user agent and IP. We then compare this new fingerprint to the one stored in the JWT. If they don't match, we know something has changed. We immediately reject the request with a 401 unauthorized HTTP code and clear the authentication cookie. This forces the user to log in again and re-authenticate. Even if an attacker intercepts or steals a user's JWT token, they can't use it from their own computer. The token contains a fingerprint that only matches the original user's browser and network. Our second layer of defense is using short-lived tokens. Our JWTs expire after just 1 hour of inactivity. This means even if an attacker obtains a token and is able to bypass the fingerprinting check by using the same IP and user agent, they have only a 1 hour window to exploit it. After that, the token becomes invalid and the attacker would need to steal a new one. The third layer is our use of HTTP-only cookies. These cookies cannot be accessed by JavaScript. This protects them against the most common way session tokens are stolen, through cross-site scripting attacks. Even if an attacker manages to inject malicious JavaScript into our site, that JavaScript cannot read authentication cookie to send it elsewhere. The fourth layer is our secure and same-site cookie attributes. The secure flag ensures the cookie is only transmitted over HTTPS, preventing it from being intercepted in transit. The same-site attribute, set to strict, prevents the cookie from being sent in cross-site requests, which protects against certain types of session hijacking attempts involving malicious websites. We also implement session invalidation on logout. When a user clicks logout, we call session.destroy on the server and clear the cookie. This makes the token immediately invalid rather than waiting for it to expire. We also generate a new session ID on every login. This prevents session fixation attacks when an attacker tricks a user into using a session ID that the attacker already knows and has compromised.
We implement 6 comprehensive layers of defense against XSS attacks. Layer 1 is our content security policy, implemented through the Helmet library. CSP is like a whitelist that tells browsers which sources of content are trusted. We configure it to only allow scripts from our own domain by setting script source to self. This means if an attacker somehow injects a script tag pointing to their malicious server, the browser will refuse to load it. We do allow unsafe /inline for scripts. We need this because React applications often use inline event handlers. Our CSP also sets object source to none, which prevents the embedding of plugins like Flash. We set base URI to self to prevent attackers from injecting a base tag that changes how relative URLs are resolved. Layer 2 is the XSS protection header, also set through Helmet. This header tells browsers to enable their built-in XSS filters, while modern browsers have XSS protection enabled by default. Setting this header ensures it's active even in older browsers or when users have changed their security settings. Layer 3 is input validation and sanitization on the server side. Every piece of user input goes through the Express Validator library's escape function. The escaping happens before we store the data in the database, so the escaped version is what we persist. Layer 4 is HTML sanitization using the sanitized HTML library. While Express Validator's escape function handles most cases, we use sanitized HTML as an additional safeguard for any fields where we might need to allow some HTML formatting in the future. We configure it to allow absolutely no HTML tags and no attributes. Layer 5 is the X content type options header set to no sniff. This prevents browsers from trying to guess the content type of responses. Without this header, a browser might interpret a file as HTML, even if the server says it's plain text. potentially causing JavaScript to execute. By forcing browsers to respect the content type we specify, we prevent this MIME sniffing XSS attack vector. Layer 6 is React's built-in XSS protection. React automatically escapes all values before rendering them.
We use several application-level defenses to handle moderate attacks and resource exhaustion. Our first defense is rate limiting with Express Rate Limit Library. General API requests are limited to 100 per IP per 15 minutes. Authentication endpoints are restricted to 5 attempts per 15 minutes. These limits prevent brute force and authentication-based DDoS attacks. The second defense is request size limiting. We configure Express to reject request bodies larger than 10 KB. Using express.json limit 10 KB and express.url encoded limit 10 KB. Since normal requests are under 1 KB, our third defense is server-level timeouts to block slow-loris attacks. We set a 30-second request timeout, 5-second keep alive timeout, and 6-second headers timeout. These settings close slow or idle connections, freeing up resources for real users. We also use request queuing to handle traffic spikes gracefully without downtime.
Primary defense against this is encryption, and we implement this by enforcing the use of HTTPS and SSL. Our application runs two servers, an HTTPS server on port 5443 and an HTTP server on port 5000. The HTTP server exists only to redirect users to the HTTPS one. To enable HTTPS, we need SSL certificates, a public certificate, and a private key. In development, we generate self-signed certificates using the node's crypto library. For convenience, the generation happens automatically when the server starts if the certificates don't exist. We create a 2048-bit RSA key pair and a certificate valid for 1 year. Self-signed certificates work for development, but they cause browser warnings in production because they are not issued by a trusted certificate authority. We implement HTTP Strict Transport Security, or HSTS, which is an HTTP header that tells browsers to only connect your site using HTTPS and never HTTP. We set the max age to 1 year. Once a browser sees this header, it will refuse to connect to a site over HTTP for the next year, even if the user explicitly types HTTP in the address bar. All of our cookies have the secure flag set. This means that browsers will only send these cookies over HTTPS connections, never over plain HTTP. Even if an attacker somehow tricks a user into making an HTTP request, the authentication cookies won't be included, so the attacker can't hijack the session. We also validate that the requests are coming over secure connections before processing sensitive information.
We have built a secure international payments portal that implements multiple layers of defense across all aspects of the application. While no system is perfectly secure, we've created a robust multi-layered security architecture that would be appropriate for handling financial transactions.